photodetector? Any idea of you having about photodetectors? At least detectors.
So photo means light and detector means to detect something.
Yeah, great. That's great. So as simple as that will detect light. Okay, detector means something it will catch. Okay, just whenever you observe just a name or any word, just you clearly observe, you will get a 50% answer in that word only. Okay, so photo and detector. Photo means light. Okay, you know that one. Light. Detect means it will collect or catching something like. Okay, catch or collect or detect something like that. Okay, device it detect. Okay, something it will detect. Okay, so here also the photo detectors are mainly collect the photons. Photons are light. Light is nothing but photons only. Okay, that will collect the photons and that will give signal, some signal, and we will analyze that signal. We can see something is there. Okay, some object is there, something is there. Okay, that is the see. We are using this detectors many applications. Okay, before going to this topic, how this will work. So first we will see where we are using these detectors. Okay, first one. Can you tell me where we are using these detectors generally in normal life, human life? You know, many detectors are there.
Bomb squad.
Yeah,
Bomb squad.
bombs. Yeah, bomb detectors and
Metal detector, sir.
sorry,
Shopping malls. Metal
shopping mall
detector.
metal detector. Okay, and hmm, tell me, gas detectors. And suppose if you are going this bomb, you know, anyway you sometime if we usually see this one bomb squad will come, they will scan whole area and they will detect something like that. Okay, that is bomb detector. And also in shopping malls also they will there is a detector. Okay, that is also sometime unnecessary means metals or some sharp things they can detect. And gas detectors also generally in our home, suppose cooking gas is leaking, we will smell with our nose. Okay, suppose if you take a HPR Indian or Bharat gas, so there is a industry, there is a continuous inline process going on to this processing of gases. Okay, they cannot use our nose, so there you need a detector. Suppose anything will leak there, whole that industry will blast. Okay, to protect that one small leakages in the industry, you need a detector, that is gas detectors. And also in chemical labs also, chemical labs or chemical industries also, something any gas is leaking or any liquid are leaking, liquid something like leaking, you need also some detectors. Okay, that is then we can reduce the damage, we can protect the things. Okay, we can find out leakage. If you find out leakage, immediately you can take care the safety measures and you can save your life. Okay, and also generally you see this one when you are going on bike. Okay, when you are going back, when you cross speed limit. Okay, speed limit, if you cross speed limit they will fine you. How they will find out you are going above 80 kilometer per hour or 90 kilometer per hour. This is also suppose place man. Somebody is unmuted and so please mute. So you are going on a bike here. Suppose you are going on a bike here. So they will send some light rays here. Okay, they will send laser beam or some very focused beam they will send. Just generally use laser beam. Okay, they will send here. Okay, when you are object, that light will reflect, and so if there is no object it will transmit, right? If there is an object it will reflect back. Depends on the speed of this laser light, how much time it is reached object and how much time it is reflected back as a detector. Okay, so once this signal is catched out, so they can estimate how much speed you are going. Okay, you are in limit or out of limit. Okay, then they will give you a fine. Okay, these are detectors and many detectors are there. Suppose if you have a this rail bridge is there. Okay, rail tracks. Okay, if there is a crack in the track. Okay, so suppose you will send some rays, sound rays or ultrasonic rays or something like that. So they will find out what is where you observed cracks. Okay, some there is a, if you are sending some waves here, there is a destruction of wave, but on the same time on the other track you will collect the this wave, but here you will not collect that beam. So analyzing these two beams, you can estimate you are finding some crack or some defect in a track. Okay, there how much distance it was, some defect was there or some cracks are there. So you can analyze the data and you can protect. You can save. You can repair that tracks, railway tracks. Okay, and also if you go to some any manufacturing, suppose here we are doing. Suppose if you do small things manually, that is okay. In industry, automatically they will do automatic manufacturing. Automatic. Okay, in automatic system we cannot check everything, all machines only take care of this fitting and manufacturing whatever. Okay, so there also you can send some light in the object or any body, you want to check it is perfectly manufactured or not, then you can send some light and you can see, you can observe the what is the problem and where some defects are there. You can using these detectors you can observe, you can find out and you can solve the problems. Okay, so in regular life we are using many types of detectors. Okay, but here mainly in this semiconductor photodetectors we are using only photons, only light to detect the some object or something like that. Okay, so that we'll see how these photo detectors are working. Okay, so it is simple, but simple and just like PN junction. And detectors, these photo detectors have many applications. And also suppose you are fabricated on transistor. Okay, transistor PNP or NPN transistor. Okay, whether this transistor properly manufactured or something, it is performing normally or not, or if you make any device it is perfectly perfectly manufactured or any defects are there, you can compare. Ideal one photo detector is there, actually perfect photo detector, take it is a reference and you can analyze this data, you can measure the data of this transistor and you can use the photo detector or photodiode. You compare results and you can correlate the data and you can see where the problem is there. Okay, that way also calibration purpose also you can use the photo detectors or photodiodes. Okay, these are the applications in real life applications. Okay, so now we will see how these photo detectors will work. Okay, so is it clear to you? These are general applications you really real life daily observe these things. Okay, so in some photo detectors we have three types of photo detectors. Okay, that we will see what are the photo detectors. So to understand these photo detectors and to improve these detectors which detect the object, we have very importance. Okay, because in real life we are using many places. Okay, these are to protect human life or damage or reduce the damage. Okay, so this is the thing in photo detectors, semiconductor photo detectors, we have three kind of detectors. One is photodiode. Okay, PN photodiode. Okay, this is one type of photo detector, PN photodiode. Second one is PIN photodiode. PIN photodiode. We'll see one by one. Okay. And third one is avalanche photodiode. Okay, avalanche. These are three kind of photodiodes are available present. Okay, in syllabus. But there are many photo detectors. But in our syllabus only we have this kind of. Here PN photodiode and PIN photodiode, and third one is avalanche photodiode. Okay, PN means here we are using P-type semiconductor and N-type semiconductor. And in PIN photodiode, here P-type and this is I means intrinsic. Intrinsic means, this is we are not doping anything, just intrinsic pure semiconductor using middle of the P and N region or P and N type semiconductor. Okay, that is the PIN photodiode. Okay, avalanche diode also we will see that one. Okay, this is also just like a PIN diode only. This is also PIN, but we will take in this region, some of the region we will dope heavily. Okay, that is why this is some avalanche photodiode. We will see that one when we come to that one. We'll see. Okay, so now we'll go to the PN photodiode. You know how PN junction will work, right? Okay, is it clear, right? My voice?
Yes, sir.
Okay, thank you. So same as like a PN junction, that why I many times I stressed on PN junction means this whole, once you understand PN junction, you can easily write these things. Okay. So here also we are drawing again this PN junction. Okay, just like this. Okay, here we have taken an interface, and left side we are taking P-type semiconductor and right side we are taking N-type semiconductor. So here we are connecting P and semiconductor, N-type semiconductor. Okay. So this is just when you combine P-type, N-type, there is an interface in the middle. And we know in P-type semiconductor, majority carriers are holes. Majority carriers are holes. Okay. Minority carriers are electrons, and these are the thing. Okay. Similarly, same thing. In N-type semiconductor, electrons are the majority carriers. Electrons are the majority carrier. Holes are the minority. Okay. That is, you know, already we are discussing many in many classes. Okay. So these bubbles are holes and these dots are electrons. Okay. When you combine this one, because of the charge carrier gradient or higher density of charge carrier. Suppose if you take p-type semiconductor, holes are the higher concentration. If you take p-type semiconductor, hole concentration is very higher than the electron concentration. So that's why holes are the majority carrier, electrons are the minority carrier. Similarly, when you take n-type semiconductor, electrons are much greater than holes. Okay, so that's why electrons are the majority carrier and holes are the minority carrier in n-type semiconductor. Okay, so here because of the charge gradient, some of the hole diffuse from P to N. P to N. So once this will diffuse, it will leave a negative acceptor ionized density or acceptor ionized atoms. So similarly, when electrons leaves this region, okay, N region, it will leave a positive charge density. Okay, this negative and positive is immobile charge density. Similarly, left side towards P side, negative charge will induce, and right side positive charge will induce. That is, we have discussed already this one. This is a depletion region. Okay, this is a depletion region or space charge region, you can say. This is depletion region. Once this positive and negative charge induced are developed, so there is a internal electric field, that is direction is always, you know, plus to minus. And because of this internal field also, there is a built-in potential. Okay, this is also we have discussed. Okay, built-in potential also developed between P and N type region. So after this depletion region forming, further suppose here one electron is there, this electron want to cross this electron want to here charge, already here still inside electrons are higher concentration compared to P type, but so this electron want to go to P side because of the higher density, but they are seeing some barrier or they are seeing some height or depletion width. So electron cannot cross this barrier. Okay, similarly holes also, here P side also hole density is still higher, but they want to cross, but because charge gradient is higher, but they want to cross, but there is a barrier. Okay, suppose see simple example. Suppose here you have a this dam. Okay, water reservoir you have. Okay, reservoir you have. Here water is high. Okay, water level is there, but this water want to go but this side, but there is a obstacle here, so they cannot go. Here water are stopped here. Okay, so once you open the gates, the water will go downside. Similarly, here also same thing. Here whatever depletion region is just like a dam or bridge or barrier. Okay, barrier. That's why even electron density is higher in inside and hole density is higher P side. But because of this depletion region, they are unable to cross the barrier. Okay, so in this is the depletion region and internal electric field built-in potential is formed. Okay, that is thing done. So now if you want to send these electrons or holes one side to other side, you have to apply forward bias or reverse bias. But in our case, these photodiodes or photodetectors always work in reverse bias condition. Always work in reverse bias condition. So reverse bias means plus minus terminal is connected to P side and plus terminal is connected to N side. This is reverse bias condition. Okay. So here what is happening because of this reverse bias, electrons will attract towards the positive terminal electrons. Okay. Here also these holes are having positive charge. This will attract towards the negative terminal of the potential, right? So because of this attraction, the depletion width will increase here. Okay. All electrons, some of the electrons will move towards the potential or battery. Okay. And similarly, and some of the holes will attract towards the battery of negative potential. Because of this one, the depletion width will increase. Okay. Depletion width is increasing means electric field also increasing. This is electric field also increasing. This is internal electric field only. Now see here, internal field is electric increasing and holes and these electrons also attracting towards the battery and more charge density is induced in the depletion region. That is done. Okay, this is reverse bias condition as we have discussed in the previous class also. Now thing is we have to illuminate some light. Photo detector means, so here there is a object, you are shining some light here, you are shining some light here, then suppose electron holes are creating, these electron holes also we are drifting towards the other side and we are collecting these electron holes. Okay, what we are doing, simple thing is, first one, three steps are involved in a the solar cell photodiode functioning is same. First what we will do here, the working, first use the, we will create electron holes or will generate electron holes by light. Okay, first generate by light. Okay, what we are doing, just PN junction we have taken, we have connected that PN junction in reverse bias. Okay, after that using light we are creating electron hole pairs, second thing, after creation, after generation of this electron hole, we have to separate. Okay, separation of the electron holes, separation of electron hole pairs. If we are not separate these electron holes, this will recombine again. Okay, this will recombine again, we will not collect the electron and holes. Okay, and third thing is, okay, third one is collection of these electron holes. After separation, we have to collection of electron holes separately. Okay. So here mainly photo detector function is, we will shine light. Okay, we will illuminate light on the object. Suppose any object. In this object, we will create electron holes. After that, we will collect these electron holes. After collecting, once you shine the light, okay, how many electrons are created, how many holes are created? When you not shine the light, how many electrons are created, how many holes are created? Okay, with light and without light, the main what we are doing is here, okay, just we are taking one object, any material, on that we are illuminating light. Okay, once you illuminate light or once you incident the light, how many electrons or holes are created? Okay, in that how many we have collected, that is we will note down. Okay, first thing, after that we will switch off light and we will, this biasing is still there. Okay, on the biasing condition, how many electrons are there, how many holes are collected. Okay, how many generated, how many collected. Okay, that we will analyze with light, without light, we will analyze the electron density or current, flow of current, we will, flow of electrons, that is current we will measure. Okay, with light we will shine the light, we will incident the light and we will measure the current, first thing. And second thing, we will switch off the light and measure the current, second thing. Okay, once you measure this current with light, without light, then we will observe how much current is improved, how much current is reduced. From there we can detect the object or something object is there, so how many electrons are created, some object is not there, so how many is created. That way these detectors are used. Okay, so first we will generate the electron holes by shining light, and we will separate and we will collect. Okay, now here if you see in this diagram, so we'll shine light on the top side. Okay, we will shine here. Okay, on the throughout semiconductor will shine. Okay, so once you shine here, so here electrons holes are creating in this is bulk region. Okay, bulk region, this is bulk region, and here also we are calling bulk region. Okay, so here also electron holes are creating, and in the depletion region also electron holes are creating. In the depletion region also electron holes are creating. Here in the depletion region, we have sufficient electric field. Sufficient electric field. This electric field is what is doing this one. Here electrons are negative charge and holes are positive charge. This electric field, whatever magnetic carrier holds in end side. Magnetic carrier holds in end side, because electric field direction is plus to minus. Plus to minus. Because of this direction of electric field, the internal electric field drift to the holes towards and p side. Holes towards p side. Okay. And similarly, electrons in p side also drift towards the end side. And also we are creating electron holes in the depletion region also, right? In the depletion region also electron holes are creating. So in the whatever generated electron holes in the depletion region, so holes it is sending to p side and electrons sending to n side. So because of this drifting, only electrons are moving to n side. Only electrons are moving inside. So here I am writing again. So in the depletion region, only electrons are moving inside. That means in inside semiconductor we have already electrons. So here we have electrons, and electrons only coming to this region. That is one thing. And similarly, if you take p-type semiconductor, here p-type we have hole. This electric field drifting the holes towards the p side. That means, so here only p side only holes are coming, n side only electrons are coming, so that there is no recombination losses. Okay, so if you take another case here, suppose n side semiconductor we have electrons. So if you send here holes, what is happens here now? Suppose we are sending holes to n side. What will happens here? Please tell me. Suppose n-type semiconductor is there. If you send holes to n-type semiconductor, what will happen? Or you can take a p-side semiconductor. To p-side semiconductor, if you send electrons, what happens?
Electrons go to transition state.
We are sending electrons to p-side. Okay, it's not transition state. It will recombine, because see, electron having negative charge and hole having positive charge. So if you give forward bias, the recombination will take place. Or if holes only come to n side, holes comes to n side, now here hole and electron will recombine. And p side also, p side holes are the majority. Once electron come to the p side, this electron holes will be recombined. So this is no useful. Once electron hole recombine, we cannot collect any charge carriers. That means there is no current. Suppose if you have electrons here, there is a current. But if electrons holes recombine, nothing will be there. So you will not get the any current. Any current. That's why here we are connecting the devices in reverse bias condition. Okay, in reverse bias condition we are connecting. Because of this reverse bias, we are increasing the internal electric field at the depletion region. That you know, we are increasing internal electric field at the depletion region. This internal electric field, what is doing? This is drifting electrons towards N side and holes towards P side. So only holes are going to P side. So here holes and P side also we have holes. So holes density is increasing. Similarly, P N side only electrons are drifting towards N side. So in N side we have only electrons are the majority carrier, and again we are sending electron. So electron density will increase, hole density will reduce. So that is why we will reduce the recombination losses. Okay, that means more number of charge carrier gradient is increasing in reverse bias in P region and N region. So you may ask this, whatever this depletion region is, just a second. Whatever the depletion region is our active region. So why? Because whatever electron holes generating in bulk region also we are generating. So here in the bulk region also we are generating electron hole pair, right? In the bulk region. So here what happens? We are generating electron holes, but these holes and electrons will recombine. This here also in P side, these electrons holes will recombine. Using light, we are generating electron holes in P-type semiconductor and N-type semiconductor in the depletion region. Three regions we are creating electron hole pairs. Whatever electron holes generated in the bulk region will recombine. That is not useful for current. Okay, that is not useful for current. That's why whatever generated electron holes in the depletion region are only useful for current flowing in a circuit. Okay, that's why this depletion region only active area for photodiode or photodetector. Whatever generated electron holes in the depletion region only useful. Okay, whatever generated electron holes in the bulk region are not useful because their recombination losses are there. There is recombination losses are there. So that's why we are connecting reverse bias and drifting the electrons and holes, and we are collecting these charge carriers. Okay. Now, finally, we have generated electron holes by light. This is done. First step is done. Second step also done by separating electron holes by internal electric field. Internal electric field, we are drifting electrons, minority carrier holes from P to suppose this is N side semiconductor, this is P type semiconductor. Okay, minority carrier holes in N type we are sending to P side, and minority carrier electrons we are sending to N side. So this is drift passes. We are applying drift passes by applying reverse bias voltage. Okay, so that we can increase the number of electrons in N type, number of holes in P type. Okay, this is done. We have separated. So this internal electric field immediately, whatever after generation of electron holes in the depletion region, suppose here depletion region, here electron holes are generated, but internal electric field is there here. Okay, internal electric field, immediately this will what will do this immediately. Okay, this will send holes towards the P side and electrons towards the N side. The main job of internal electric field, it will reduce the recombination losses and it will drift the charge carriers. Okay, whatever holes towards P side and whatever electron towards N side. So we are reducing recombination losses and we are getting the current. So final step is you have to collect the charge carriers. Suppose electrons holes are coming this way and holes are coming, electrons are coming this way. So you use metal contacts. Okay, just like we have discussed in the last class, metal contacts. Using this metal contact you can collect the electrons. Okay, you can collect the electrons and holes, and to measure how much current is flowing in a circuit you install one ammeter, and in this ammeter how many electrons are flowed in this circuit. Okay, how many electrons or how many charges are flowing in a circuit? This will measure. That is what ammeter will do. Ammeter job of ammeter is just to measure how many charge carriers are flowing in a circuit. Okay, that is what how many charge carriers are flowing in a circuit for particular time. Suppose 10 charges are moving, 10 electrons moving for 1 second. Okay, that means current is 10 amperes per second, like that. Okay, so just this is an example, just like example. So it will measure current. That is the ammeter job. Okay. Now we have completed the same principle will apply solar cells also. The same principle. Generation of electron holes by light and separation of electron holes by internal electric field by connecting reverse bias condition, by applying reverse bias voltage. And after that, after separation of these charge carriers, we will collect electrons and holes using ammeter. Okay, this is the simple working of photodiode. Okay, it is very simple. Once you connect a PN junction diode, you know reverse bias condition, how it will work. Once you connect, there is a depletion region is forming. This because of this depletion region, the electrons holes cannot cross this barrier or depletion width. For that, you need to apply some biasing voltage, either forward or reverse bias. But our case in photodiodes, it will work under reverse bias condition. So we will apply reverse bias voltage. Once you apply reverse bias voltage, the electrons in inside will attract towards the positive terminal and holes in P region will attract towards the negative terminal. And because of this attraction of these charge carriers, here more number of electrons leaves this place and more number of positive charge is developed and more number of negative charge is induced in the depletion region. Because of this increased charge density, that is negative and positive charge density in the depletion region, the internal electric field increase. Internal electric field is increased. Because of this internal electric field, depletion, the potential barrier height also increase, or built-in potential also increase. Okay, that is the at the space charge region things happens. Okay, now this is the thing. Because of this internal electric field, okay, drift process will dominate. Okay, drift process will dominate. So now our job is to illuminate the light and shine the light or incident the light. Once you incident the light, electrons holes will be created throughout the semiconductor, P region, N region, and a depletion region. But P region, whatever generated electron holes will recombine with holes in the bulk region. Similarly, in the N side also, this generated electron holes, these holes will recombine with electrons. So this will not useful for current in a circuit. Okay. Now thing is, because there is no field to separate in the bulk region, there is no electric field to separate. But in the depletion region, we have sufficient electric field. So whatever electron holes generated in the depletion region will be separated by this internal electron. So in the bulk region, we don't have any electric field or anything. So only internal electric field is developed in the depletion region only. This depletion region, in this electric field immediately separate the electron generated electron holes. This internal electric field sends holes towards p side and electron towards n side. So only electron moving to n side, that means there is electron and n side also we have electron, so electron density is increasing in n side. Similarly, p side also only electric field drifting holes towards the p side. So in P side also holes are the majority carriers. On top of that, we are sending only holes to P side. That means hole density is increasing. That means if you shine the light, if you apply reverse bias, we are increasing the electron density, hole density. So using this reverse bias condition and using internal field, we are separating charge carriers in the depletion region. So bulk region generated electron holes are not useful for current. So only generated electron holes in the depletion region only separating. These are the useful for current. That's why our active area for a detector is only depletion region. Only depletion region is only useful for detecting the light. Okay, that is the thing. After that, using this internal electric field, we are separating, and using metal contacts, we will collect the electron holes, and using help of ammeter, we are measuring how much current is flowing in a circuit. This is simple working of this L-8, this photodiode. Tomorrow we will use the band bending diagram, and we will understand after the IV characteristics. Okay, that is also very important. How we will measure the current, that we will see in IV characteristics. Okay. Is it clear to today class? Any doubts you have, please raise your hand, or you can ask me, please. Any doubt, any problem, anything? Is it clear today class?